Alrighty. Well, thank you for joining us today. If you are here today, my name is David Lee, and I'm coming to you from the Federal Laboratory Consortium, where I am the regional coordinator for the East Coast, the Eastern region, Northeast region of the FLC. Today, if you're joining us, we are exploring Lincoln Laboratory facilities, specifically the Optical Terminal Verification Testbed. And we're going to talk a little bit about that with some of the people who run the testbed. As you probably know, Lincoln Laboratory is affiliated with MIT, which is full of very, very smart people, far smarter than me. And I am glad to be introducing some of those very smart people. And I will start by introducing them and reading their bio, a little bit about them. Again, my name is David Lee, and thank you for joining us. Today, joining us from Lincoln Laboratory from the OTVT, the Optical Terminal Verification Testbed, is Jonah Tower. Jonah is the group leader for the Advanced Lasercom Systems and Operations Group at MIT Lincoln Laboratory. The group supports all phases of the development of lasercom systems and technology, including architecture and standards definition, early and advanced prototyping and demonstrations, and critical testbed infrastructure. Jonah joined the lab in 2003 as a software engineer and moved to the communication division in 2008, where he has worked on advanced, complex lasercom prototypes as software architect, systems engineer, and program manager. He has been a part of the leadership team for the group since 2019. In his free time, Jonah enjoys spending his time with his kids, running, mountain biking, hiking, and snowboarding. He is currently struggling to learn how to surf. So as you can tell, Jonah is an underachiever. And speaking of underachievers, we also have Molly Hsu. Molly is a test lead at the OTVT and is in advanced lasercom systems and operation group at MIT Lincoln Laboratory. She's been a technical staff member at the laboratory for over 10 years with background in optics and system engineering. She's the optics lead for all OTVT test events and leads the team for various development, integration tests, and operation for the testbed, or of the testbed. Prior to her time at MIT Lincoln Laboratory, she worked at Northrop Grumman on high energy lasers and solid state lasers, including the airborne laser program. On her spare time, she enjoys traveling with her family and running, especially doing marathon and half marathon races. This to me is very impressive that both these people run, because the only thing I usually run after is the ice cream truck. So I am supremely awed. And if you had the chance, reach out to Jonah and Molly and look at their bios on LinkedIn. They are high speed folks. And without further ado, I will turn it over to Jonah and Molly to talk about the OTVT. Thank you.
Good afternoon, everybody, and thank you, David. Appreciate those intros. I'm really excited to be here today and get a chance to talk about the Optical Terminal Verification Testbed going forward. We'll refer to that as just OTVT for short. This is a testbed that we in our group have had for almost a couple of decades now, and we'll talk a little bit more about the legacy at the end of the briefing. And it's an asset that we've invested in quite a lot. It's a very, very capable testbed. I think that will come through in our sort of short briefing here. But this is sort of a bit of a coming out for us in that we have sort of a new offering at this point where we're now not only be able to support government projects, but also have activities independently with industry direct. And we'll talk a bit about that as well. So with that, let's jump on to the first chart here. The first thing I wanted to talk about is, why lasercom? My group, our mission statement is sort of summarized in the forewords at the top of this title. We do lasercom technology development, systems, architecture, waveform development, and we do that primarily in support of national security. That is MIT Lincoln Laboratory's primary mission, and it is also the mission of the group. And on the left here, you can sort of see some architectural concepts for how the government might use lasercom, for different configurations. And the reasons that the government is interested in lasercom are sort of threefold. One, we can do very high data rates over very long ranges. There's what we call low probability of detection or interception. There are also nice anti-jam qualities of lasercom systems. In the commercial side, you might think of that as I have basically infinite spectrum and thus infinite bandwidth. And so there's a corollary to that second bullet. And then, of course, the other part of this is that we can have very low size, weight, and power systems comparatively to equivalent RF systems. And those are really nice qualities for lasercom communication systems. We have seen this technology grow quite a lot. We've actually been involved in it for a long, long time here at Lincoln Laboratory. But just recently, companies like SpaceX have, on the commercial side, been successful with this. In addition, NASA in the last few years has had some really interesting demonstrations. Unfortunately, I won't get a chance to go into a lot of that, but I did want to set the stage with where this is and where we're going. So as we introed, right, our group works in all the phases of this, but today I just wanted to talk about the testing aspects of it. So free space optical communication requires quite a bit of testing, both in the functional side and in the performance side of the equation. The simple sort of analogy that I make is, people are very accustomed to optical communications through fiber optic. That is the backbone for the modern internet. And it's even becoming, quite prolific as the last mile. Many people have Fios in their homes. Fiber optic comm, really great success, lots of benefits to that. But if you have to go a long distance or in an environment where the infrastructure is not there, carrying that spool of fiber is a difficult problem. And so in essence, what we're doing is we're moving the fiber and still doing the same comm. But by removing the fiber, we take on a lot of complexity. There's performance parameters, power, imploss, wavelength, timing of just the optical signal alone. Pointing acquisition and tracking, or PAT as we call it, is very complex. And if you look at the bottom right of this chart, you'll see, from the moon to the Earth, your typical Ka spot size is thousands of kilometers across. And so even though that is a long distance, it's relatively easy to point that compared to the same type of communication if you were using laser comm, in this case, the C-band with a 10-centimeter aperture, in which case you've got a 6-kilometer beam that you have to point from a very vast distance. And then the waveforms themselves and the implementation, the definition and implementation of those are themselves very complex and require very detailed testing and verification. So a testbed environment like OTVT really needs to emulate quite a lot of things. There's a range, a relative velocity aspect to this. If you're going through the atmosphere, there are turbulence conditions you need to account for. And of course, your platform upon which your terminal exists is going to have its own motion, and then there's going to be induced beam jitter. And so OTVT really is a state-of-the-art testbed that tackles all of these aspects of laser communication. Go to the next chart. So just a quick outline here. I'm going to talk a little bit more about the capabilities of OTVT. I'll then hand it over to Molly, and she's going to dive into the test categories, some of the things that we can do for data products. We've got a little case study on T-Bird, and then we'll wrap up talking about sort of the facility, the logistics of testing, and then of course this new capability for us, which is the Lincoln Laboratory test agreements that allow us to offer this test bed a little bit more widely, and then we'll wrap up with a quick summary. So we go to the next chart. So OTVT, in my opinion, and I've seen a few test beds, is really a unique national facility. We have exquisite testing capability, and we can do quite a lot of things with this test set that I haven't found anywhere else. As an FFRDC, or a federally funded research and development center, MIT LL does provide unbiased assessment of both industry and our own terminals for the government. That is core to our mission. We tend to focus on interoperability testing between government standards, though we have also started to pull in other standards that you can see more commercially available. And what we're really trying to do here is set up a gold standard implementation and test bed against that implementation, against these standards, as a way to realistically represent both the space and terrestrial environment and provide an opportunity for terminals that are being developed to get a very detailed characterization of how they're performing against the known standard. So we go to the next chart. And there's sort of 6 functional elements to OTVT. We'll talk a bit more about the channel emulation that's up here in the top left. It's sort of like the big beefy front end of the system. I already mentioned pointing acquisition and tracking. That is one of the more complex aspects of a laser communication or a free space laser communication system. And so we do quite a lot of work to make sure that we've implemented that. That's mostly done in software. So you see the canonical rack of equipment representing that. On the right top, there's ultimately a comm aspect to this. OTVT tests quite a bit more before you even get to communications. And we have several modems and government furnished equipment as well as networking equipment behind that allow us to do full end-to-end verification on the communication side. And on the bottom, you really sort of see some of the workhorses of the test bed itself. There are a lot of optical components. There are a bunch of electro-optical components as well within OTVT. We have a pretty sophisticated fiber switching fabric that allow us to interoperate or switch in and switch out elements throughout the testing procedure. We have a networking backend. We collect a lot of data in this system, and of course we want to be able to archive that and then post-process it. And on the bottom right, we've invested quite a lot in software, both for the control side of the test bed, so that we can automate test setup, but also on the post-processing side, pulling telemetry both out of the test bed and the comm system as a way to then produce products and really give terminals that are being tested a thorough scrubbing and then some detailed information on where they're succeeding, where they may have challenges, and certainly one of the key things in any comm system is where the margin might exist. So we go to the next chart. So OTVT, on the top left is the sort of CAD diagram of the test bed itself. I've extracted out of this all the back-end stuff that I just talked about. We use the phrase TUT, or terminal under test, as the guest terminal, and they'll come, and there's a table there in the bottom right of that CAD picture. We can host a pretty large system on that. We have definitely put things in the sort of meter by meter by meter class on that test bed, and we've also tested things that are quite a bit smaller, and our use case or case study will show that. The main optics table in the middle is really where the test bed emulates the channel. We can bring full power beams into the system and do the power reduction. We'll talk a bit more about that. And then we have a modular set of plates that allow us to bring all sorts of instruments, fiber launches, different bulk optics. We can put different filters and steering into that. So we've got a very capable stable of equipment that we can then deploy to emulate all sorts of different channels, and we'll talk a lot more about that as well. In order to keep the test bed fully up to snuff at all times, we have our own calibration table, and that allows us to independently stimulate the whole system and verify that we're operating at a nominal state. And then not pictured here is a bunch of rack equipment. But at the end of the day, really what the test bed is doing is emulating the full channel from the terminal under test to a partner terminal in the far field, and we emulate that as well. Go to the next chart. So testing overview, at the you bring a terminal in, there's a whole bunch of logistics with that. Usually that's crates of equipment depending on the scale of what's being done. We then set up the emulation, channel effects, platform jitter, and we'll talk a bit more about how we do that. We then implement representative laser comm terminal behavior. That is, the pointing acquisition and tracking aspect is a big part of what goes on in the testing, but the back-end comm as well is implemented behind that. And the testing sort of builds in that same way, right? So we're looking at the optical properties of the terminal under test. We're implementing, the pointing acquisition and tracking performance and the communication performance tests. We have reference terminals, or reference modems of different grades to be able to emulate, what a characteristic or what a standard sort of terminal might look like. But then we have very high fidelity tools to be able to then measure like how well is the system performing that is under test above and beyond, performing with a compatible characteristic system. And really, what we do, we sort of do a little bit of a crawl, walk, run. Typically testing will just start with, fiber to fiber modem tests, which would exclude everything that's shown here in the top, in the left side of the chart. Go to the next chart. So what can we do at OTVT? One important thing that we are able to do here is we do full aperture testing. And so we can test apertures all the way up to 16 inches in diameter. That's a really big telescope, but we do have examples where we've gotten pretty close to that. We have very high quality optics in our system. We've worked really hard to make sure that we've got a low wavefront error. We have low polarization dependence. The whole system is in a clean tent, so we have a very clean and highly characterized optical setup there, so that we know where our baseline is and then we can measure up against that. One thing that is unique about OTVT is that we can operate with terminals at full power. And so, over a long distance, right, even though we're very, as we say, swap efficient, right, you still have a good amount of power that needs to leave your aperture. And if you're trying to send a beam from the moon to the Earth, that's a lot different configuration than if you're trying to go 2 feet across or a few meters across the room. And so most test beds will operate at a very low power mode to do this, but at OTVT, we have the ability to operate at full power mode. And that's really important when you get into these small optics, because the thermal characteristics induced with those high power configurations can really change their results. And so that's one of the things that we've done a lot of work to do, is to make sure that a terminal under test can operate at their absolute full power modes. Pointing acquisition and tracking, I've already highlighted a lot here, but we cover the full sequence. We do have sensors throughout the test bed. Molly will talk a little bit more about those that can characterize the different stages of pointing acquisition and tracking, and how the beam is behaving under a whole slew of conditions. And then what we're able to do is emulate what the terminal under test would see from the far field by dynamically attenuating the beam that is then sent into the terminal under test. And so we've got very characteristic conditions to be able to test with. Again, we do far field emulation. We can implement fading, like I said, platform jitter, and then we can also do point ahead, right? So in laser communications, the beam is so narrow, you have to actually send the beam out ahead of where you receive from to make that happen. And then the Doppler characteristics of different configurations. If you imagine, low Earth orbit satellites in cross-planar communication links, they're going to have a very high Doppler relative to the wavelengths that they're operating in, and we're able to emulate and characterize how terminals perform in all those conditions. And again, on the whole communications suite, we have very detailed implementations, highly instrumented, modems that allow us to then really dig into all the details of the communication implementation on top of the beam itself. If we go to the next chart. So I'll hand it over to Molly, and she'll dig into a lot more detail about the testing and the data that we can produce out of that.
All right, thanks, Jonah. So Jonah gave a great overview of the OTVT, and I'll dive in a little more details of tests and some sample data collections that we do at OTVT. So first, I'll describe a little bit about OTVT test categories. Generally, we divide into 3 categories. So first is the fiber-to-fiber comm test, or modem-to-modem test. The second is free space optics and a PAT test. And lastly, we do a full free space comm test here. So here I'm highlighting some of the test names that fall under each category. So in first category, we call it fiber to fiber test. And this test demonstrates the interoperability between the 2 modems. So in this test, we connect our modems to a TUT modem. And with a fiber to fiber connection, it does performance testing on a TUT modem without nonlinearity and the PAT impairments that we may see with the free space. So we can perform fiber to fiber tests when the TUT modem is in an early integration phase, and it can take around 1 to 2 weeks to perform the full suite that I highlighted down here. I am highlighting various test names on this table, and what we're trying to achieve during this test, and as you can see, we're looking at the wavelength, transmit, and receive performance, and we look at the implementation loss of the TUT receive in fiber for all the data rates, and we can do this with and without fade channels. The second one is a free space optics and a PAT test. So first, let me describe about the optics test. We're measuring the TUT transmit's optical performance through this free space channel emulator. And for this test, we need a TUT front end or optical module in the optical source. So it doesn't have to be a modem. But this test can take about 2 to 3 days, which includes the aligning the optical module with our channel emulator on the test bed. And we can measure wavefront polarizations and power. Then we move on to point and acquisition tracking test. So on this test, we need the optical module, obviously with the optical source, but also one that has the gimbal and tracking capability. So TUT should have the PAT control software and algorithm ready to execute with our free space simulator. And we verify the point ahead capability, acquisition search, or the full acquisition sequence, and also introduce the link impairment, such as what Jonah described as a jitter, fading, control dropouts, and we do the ramp down and up. And we're testing out tracking performance of the touch system. And lastly, once we check out the modem and the OM separately, we do the full free space comm test. We do that against our channel emulator and the modem. So this is a really full end-to-end testing of a full terminal. And we test at the full power with and without channel impairment. And the full suite could take about a week and a half to 2 weeks to complete. And in this test, we're really looking at touch optical spectrum. We look at the closed loop point ahead measurement. We measure the channel error rate of the transmitter. And we do that with a typical receiver and free space link, and look at the waveform. We measure phase noise, jitter, and a whole suites of other tests. We're looking at full testing of both performance and interoperability of the touch. So here I'm walking through how the terminal. Let me just play. There you go. Here, I'm walking you through how terminal beam will propagate through the free space testbed through various optic systems. So once you send the beam to us, we first receive it on the LBSA with large beam steering assembly. 96% of the beam goes into beam dump, and then it goes 4% gets reflected into our 12-to-1 diameter, 12-to-1 demarcation telescope assembly. First, it sees the attenuator, and then some of the beam gets sent to the transmit power, so we can measure the power measurements. And then some of the beam gets transmitted through and goes into the fast steering mirror, where we're emulating the jitter profile. And then once it hits the fast steering mirror, it gets reflected, and some of the beam gets captured into the wide field of view camera. So we look at the beam profile at the near field of the top beam. And then it goes into other relay optics to further reduce or magnify the beam. And it goes into a whole suite of the sensors that we have in our test bed. Some of them includes narrow field of view camera to look at the beam profile. We send the beam to the wavefront sensor, so we can look at the optical wavefront, and then lastly it goes into the receiver FLA to go into the modem. So next, I will describe a little bit of the test data that we collect. So for optical characterization tests, here's some screenshot of the data we collect with OTVT. And this is the data we actually collected using a surrogate terminal that we have it on a test bed. So we look at a terminal's transmit beam on a narrow field of a camera, and we characterize the beam size and the pointing. So this allows us to look at the far field divergence and the beam's full width half max value. And then we're monitoring the transmit and receive power that are measured using free space power meter on the test bed. We also do the polarization measurement. So it's important to know if you're transmitting correct polarization and strength of the signal. So we measure that with the beam polarizer. Here's a sample data, simple jitter file we use to emulate the motion using the fast steering mirror. So we were seeing about 10 pixels of a beam size, or about 60 microrad. What I'm not showing here in this chart, and we do this as well, we want to look at the beam quality of the a wavefront of quality of the beam, so how good of the beam is, and we do that with the wavefront sensor. And we also measure optical spectrum using the high rate OSA as part of the optics characterization. So to establish an optical link, our goal is to have two terminals, terminal A or terminal B, with the narrow high power beams stabilized and tracking each other. So here's a sample of the path sequence where we utilized our surrogate terminal that we had it on a top table to see the beam move from coarse track to fine track. So this is a real OTVT measurement where we're seeing changes in path states and changing from the coarse track to the fine track. So left axis is a total power and right axis is a terminal beam angle. Here, a user terminal initializes and scans using beacon, and user terminal, which is us, OTVT, is sending the beacon, and you can see the power coming up here indicated in blue. So now we're in open loop scan, and then you have the beacon power, which is in blue line, and terminal beam angle is still off from the center, which is indicated in pink. And once surrogate terminal or the remote terminal sees the beacon, it turns back to OTVT, to us, with the coarse tracking. And then OTVT changes from narrow beam it changes to narrow beacon to narrow beam, and then you can also see the terminal beam angle change from a large angle to small angle. So you can see that in the pink here. So we're now in an acquire and course track state. So once the terminal sees our narrow beam, we get to the terminal into center. We're now doing a fine track state, and you can see the comm power come up in red here, and the beacon, which is blue, drops in power. So now we're in a fine track state. So we have established the comm with the both terminal. So you can see the whole path sequence. It's changing in the states, and power level changes from over to beacon to comm quickly. Here's a close look at the path state regression test we conduct. Also, this is the data which collected using the surrogate terminal. So here we start with the Y beam in beacon mode, and then once we acquire, it changes the narrow beam to the comm signal. And we're now changing variable optical attenuator. So using the optical attenuator, we're ramping up or down. First, we're doing the down power from one terminal. So it could be drifting off, or there could be a jitter due to atmospheric turbulence. So this is a ramping it down in power. So this shows the ramping down, and then we hit the point where it's no longer an acquisition. So now the comm power regresses to beacon. So once we ramp to attenuation back on, where our signal is going back up and we have more signal, we are able to reacquire, so following the path sequence transition, to go from the beacon power to comm power again. Now to move on to free space comm test. So we want to look at the terminal receiver's performance. And channel error rate is a standard metrics for communication performance, and it looks at the ratio of error bit rates to total transmit bits. So this measurement allows us to determine how well the terminal A or the modem will work with our different terminal, another terminal. So we perform this measurement using two different transmitters. One is the reference transmitter, which is a really ideal modem, and has 3 modulators to tweak up to get the best performance. We use this to measure the receive and the terminal receives implementation loss. And the other one is a test modem, which is a single modulator. And this really modem is used to demonstrate the interoperability. You can see a simple full rate measurement here on the right. So this measurement is from surrogate terminal transmit to test modem receiver. So surrogate terminal transmit to the test modem, the receiver, and a power on x-axis and the CER measurement in y-axis. You can see the test modem in green and the reference modem in red. It's a CER curves against the quantum limit, which is the theoretical best performance you can get. For the test modem curve, we're showing the test taken at a low power. However, we find most of the issues or degradation at the full high power. So to measure, to make the test modem as realistic as possible, we're emulating the high power impairment on the transmit signal. We do this by using the amplifier and a long spool amplifier. You can see this on the diagram here. We're trying to find a current that is good match to remote modem, and we're setting amount of changes using amplifier's current drive level. And as you can see in this lower graph here, the transmit implementation is increasing as a nonlinear phase shift increases. Then we also characterize the terminal's waveform to verify if it is good enough to do interoperability. So we're looking for how well did they build it, the terminal they're bringing, how well is it testing against another terminal. So we measured the terminal's transmitter imperfection, which you can quantify as an implementation loss. So some of the transmitter imperfections are due to pulse imperfection. And as you can see here in the eye diagram, we see optical nonlinear phase, which is shown in a phase versus time in the IQ constellation diagram. And once again, you can see it in a nonlinear effect at the high power rather than in the low power. Implementation loss is important in the communication because it's a part of the ERP and the link budget. And we collect this full information of incoming electrical field waveform transmitter using the what's called coherent receiver and the high speed scope. And then we do the implementation loss calculation using the software analysis. So let me talk to you a little bit about the T-Bird case study. So T-Bird terabyte infrared delivery was a CubeSat that launched back in May 2022. This is a CubeSat in LEO and has a 200 gigabits per second transmit, the downlink capability. And T-Bird really showcased the high data rate capabilities of LaserComm from the 6U CubeSats in low Earth orbit. And really the T-Bird downlink data at the download data at the highest optical rate ever achieved by the NASA. So prior to finalizing the performance checkout, T-Bird came into OTVT, as you can see it here in the picture, made several optics measurement with us. Now, this is a really interesting case study because we normally do the testing at the full terminal level, and what we did with T-Bird is sort of outside of intended OTVT testing, which it's different than the traditional terminal-to-terminal interoperability testing. But however, we were able to pivot and come up with the testing that with the very minimal setup changes to support the T-Bird testing. So here's a picture. And one of the optics measurement that was done in OTVT was a divergence measurement that we did. And the T-Bird transmit beam here is shown in our NFOB, narrow field of view camera, and multiple frames are processed to generate this average and shows the stability of the measurement. So we take this beam and we plot intensity distributions to Gaussian equation. And you can see how well their beam fits against the Gaussian curve in the chart here on the right. And we're looking at the far field divergence of the beam, and we're looking at the full width half max, which we calculate that from the 50% peak intensity. So testing at OTVT really gave the T-Bird team confidence that their system will work in the orbit, and they were able to verify the performance is what they were expecting. So it was a really good surrogate to do a testing with us prior to launching on orbit. So now it's a lot of technical details, but I'll hand it back to Jonah, and he'll discuss some test event, logistic, and test agreements.
Thanks, Molly. Yeah, so lots of things go on inside of an OTVT test event. And so one of the things that we're trying to show here is how do you think about that in the context of your program or your development life cycle. Along the top of this chart, there's sort of the standard notional program timeline, starting with RFP, awards, systems requirements review, preliminary design review, critical design review, et cetera, et cetera. Just giving folks kind of a context that may or may not apply depending on the world that you work in. But OTVT, right, as we highlighted, kind of tests at 3 stages, if you will. 1, the optical module level, 2, the modem, and then of course ultimately the goal is to get to full optical terminal testing. We can tailor tests and test plans around different elements of that. Here's sort of an example approach. You might at the end of a breadboard effort want to do some sort of rudimentary or very early integration testing modem to modem, and that's sort of shown here with test event number 1. You might want to just characterize your optical module and understand a little bit more of how it is configured and performing. That's somewhat akin to a little bit of what we did with T-Bird, and that's sort of shown here as test event 2. Traditionally, before we do full, integrated optical terminal testing, we would do fiber-to-fiber testing of a final modem. There's quite a lot that can be, burned down at that level long before you get into a more complex test environment. Nonetheless, that can often happen days, if not just the week before a full test event. So sometimes test 3 and 4 might collapse down into a single large test campaign. If you build the next chart, and so we can characterize, or we can customize, how the test flow works within a programmatic life cycle. And then within a given test event or around a test event, as it turns out, there's also quite a few things that need to happen, right? We'll establish a baseline with a customer as to exactly what do we want to do in a test. And then we'll help develop a set of test ConOps. That's a very, engineer to engineer type of task. And out of that, we ought to come out forward with a test plan, a mutually developed test plan. Lincoln has quite a lot of test procedures already, and they're very mature, and you saw the list of those earlier in the briefing. Nonetheless, they almost always require some modification for a specific set of testing. And so we would develop those and finalize them. Some kind of test vector, we use this term to, communicate the idea that maybe you've done some measurements and you send those into our system, or we've got a waveform sample, whatever it is, but we might do some exchange of technical information prior to really locking in the configuration, and then we will run a set of dry runs on our end to ensure that the test procedures are really ready to go, and importantly, that our configuration is locked down. So we run all that before we'll do a test readiness review. A test event can last, anywhere from a week or so, depending on the scope of it. We've even tried, done some in the sort of couple of days class, but they might run, multiple weeks depending on the scope of the event. And then, we'll typically provide a formal test report with some early read aheads and even day of read aheads as the test event rolls out. And so this is sort of like the canonical test flow for any given test event that we might see at OTBT. Go to the next chart. So logistics around this, I won't brief the whole chart here, but there is quite a lot of coordination. There are a lot of moving parts in a laser comm system. There are probably twice as many moving parts in the test event, if not more. And so there's a lot of work that goes into doing that. There are parameters that the terminal under test needs to put into the system. Those are all defined in a document that I'll talk about in a couple of charts called the OTBT ICD. There are a lot of documents that get finalized, everything from, what tests are we going to do, when are we going to do them, test plans associated with that, and then of course the procedures, that will need to be tailored for any event. Those often still get redlined in the test events themselves. But we do try to get them highly mature, in advance of the test itself to ensure a very successful event. And then, there's some reporting, often, we work in PowerPoint here, but we've done other documents, as part of that. And then data sets can also be made available. Security posture is very important to us, of course. Our facility can operate at the collateral secret level. Testing typically is done at the unclassified level. Other test levels can be achieved, and we certainly will work with partner organizations to make sure the planning around that is all done appropriately. We do have our own standalone network for testing, and that's how we can, collect data and make sure to firewall that off from folks that don't need to have access to it. We can support standalone classified machines to allow for higher levels of data processing if that were necessary. But generally speaking, we operate, all the test data is held at the unclassified level. Go to the next chart. So the ICD, the interface control document for OTBT, is a pretty mature document. As of the generation of this chart, we're already at 2.1. This really details everything about the test facility, from how you get off the loading dock to what the environment is like inside of the test lab itself. It covers all the functional and physical interfaces, covers the data types and how we will handle file transfer. Here are a handful of highlights out of the document. It is a clean room. We have power of different types available. The terminal under test sits on a test bench itself. And there's specific orientation and sort of geometry associated with that. That's all detailed in the document. We can optimize the test set to handle, sort of the expected output power of the terminal, and that's part of, detail, or the procedures for that are detailed in the document. Time matters a lot. We didn't talk about it very much today, but when you're trying to point over vast distances, you need to have a very precise amount, measurement of time, and so we provide GPS time throughout the test bed and also to the terminal under test, so that all of our data sets can then be synchronized. And otherwise, we work really hard to minimize the connections between the TUT and the test bed, other than the interface that's being tested, just to really emulate what it would be like to operate within your target environment. So if you go to the next chart. So the facility itself, we've shown different CAD representations of the middle. Now we're taking a bird's eye view, so you might have to sort of twist your head a little bit to see what you've already seen there. You can see there's sort of these squiggly lines that represent the boundary of the clean room tent around that. We've got laminar airflow throughout that facility, so we have a really well-controlled environment for where the optical aspects of this testing occur. On the top left is where we have the away team bench, if you will. There is equipment rack space there for your own equipment to come in. There's a couple of workstations where test operators can actively operate their equipment as it's under test. There's another facility to the bottom right here, not shown, but there's additional space for staging and further equipment if needed. And then on the top right is where the OTVT team will sit during operations. There's a couple of workstation areas there where they can really monitor and fully control all aspects of the test bed. Not shown here, but there's a set of comm equipment so that, with headphones, both sides can readily communicate to one another as they go through a test procedure. And we've, again, had several events in this, this configuration, and it works quite smoothly to be able to execute in this environment. Go to the next chart. So I mentioned already, MIT LL now has test agreements for some of our test facilities. We have one of these, or at least templated for OTVT. This really allows, non-government programs to come into the facility and be able to use this, to support their technology development. It's a non-interference basis with our core laboratory work. As you can see, there's a long set of processes associated with getting a particular test event up and running, but there are still opportunities, to be able to use sort of some of the downtime, if you will, and that's really what these are about, is making that opportunity available. Any domestic, so U.S.-based organization that's non-governmental can reach out and see if we can set up an agreement depending on the nature of the technology that you're trying to work on. And then here's the contact information for how to reach out to us. I think someone will put the link in the chat in case you can't click on it here in the slides. And then we also have a handful of videos that sort of summarize some of the pieces that we've talked about today. Go to the next chart. One more. I already alluded to, I'm pretty proud of this test bed. One of the things that I haven't really talked about, though, we were introduced so kindly at the get-go by David, is there's a lot of important people that are super smart here. They are part of the, the test bed team. With the test bed itself and the team that supports it and runs it every day, and then their reach into the group for other folks that build these sort of systems, we've had a lot of success. I think of coming to OTVT not just as an opportunity to kind of get graded. That is an important part of interoperability, is sort of how well are you doing against a given standard. But generally, every terminal that comes through here, or certainly every team that comes through here, like their terminal matures through that process. And that is something that we pride ourselves on, is because we're so well instrumented, because we kind of have a really detailed knowledge of how the systems work, we're able to then feed that into the terminal under test team, both in preparation, right? So there's a long prep tail for this, but while they're here. And so you can sort of see a list of some of the things that we've seen. It's interesting, every time we've sort of thought we kind of found the last possible way to make a challenge or, quote unquote opportunity in how to implement LaserComm, there's still another thing that we discover. But there are lots of details in these things, and it is tricky to get them right. But that's sort of what OTVT is really trying to do, is help that cutting edge development get over the finish line, so that then it can become much more readily available and a commodity asset. Go to the next chart. So OTVT itself has its own sort of future look. We have a history of programs coming in, and every program has often required one upgrade or another. Currently, or just recently, I guess, we've been expanding our wavelength flexibility. I think at this point we cover almost the entire C-band. And then we're starting to, we have the capability, we're continuing to enhance it what we call A/B switching, right? So often there's an A side and a B side, and two A terminals can't point at one another, or two B terminals can't point at one another. But you see terminals that are sort of ambidextrous, and OTVT is as well at this point. Ultimately, what we want to do is be able to modularize more of this. There's been quite a bit of investment recently on this that allows both new modems and a broader range of terminals to come in. The T-Bird case study is really, an interesting one where that sort of came out of left field for us, but the team was able to really respond. And so I think we can already see the benefits of that investment. And there's sort of more exotic things like multi-aperture terminal testing, whether that's a terminal that does some kind of multi-access capability or multi-function, and so these are sort of a little bit outside of the bread and butter of OTVT, but we're starting to think about how we would approach those kinds of tests. And I already talked about the off-contract test agreement mechanism, which is new to OTVT in the last year or so, but it is an exciting opportunity to be able to make the asset available. I think we have one more chart just to summarize. So independent testing, I think, is really critical to confirm, different vendors have implemented interface requirements correctly. It is really powerful to have open standards. They're very complex. They're hard to develop the standard. It's hard to develop the terminal. And sort of having an unbiased test set is something that really can make success in that area happen. OTVT, it's got a long history, very high fidelity. We can do terminal level, like I said, at full power and at full aperture testing. We can test the functionality of the system at many levels, and we've got really detailed performance characterization across the whole spectrum of technology that's required to implement LaserComm. We do emulate the full channel, and we can do quite a lot of different emulation in that, as well as implement the remote terminal PAT. And again, these are sometimes the most complex parts making these links successful. And then, of course, at the end of the day, we're trying to set up a communication system, and we can assess that very completely, as well as check the performance on those things. And I just got done talking about, I'm personally very proud of the work that we've done with this test bed, and I look forward to continuing to do that as we see LaserComm, really taking off, in many different venues. And that's a great success story from my point of view. So that's what I had, and Molly as well. David, I'll hand it back to you if you have any questions that you want to kick to us before we wrap it up.
Jonah and Molly, thank you so much. That was a ton of information. It was very well presented. Thank you. Amazing pictures. I'll be honest with you, it's pretty much Greek to me because I'm actually more of a biochemist. So this is literally, it's a lot of math, it's a lot of Greek. So very impressive. But I was able to follow along with some of that. And with some of that, I'd like to ask you some questions with regards to testing, if that's okay. The first question is, you mentioned the TUT. Is it stationary relative to the OTVT, or can it move on a TUT table?
I can answer that one. So TUT is stationary relative to OTVT, so it sits on the TUT terminal, and we can test point ahead and Doppler capabilities, but need workaround to test algorithm, and also a line of sight is emulated by fast steering mirror in opposed to a bipedal. So it is stationary, and we looked at the options to do the slewing or moving of the TUT table, but we have not implemented that.
Speaking of the TUT table, can the OTVT accommodate more than one TUT?
Do you want me to take it?
You can take it.
Yeah. Sure. No, we could only do one test, one terminal at a time at this point. We ruled out the design for more than one due to the cost, and also the space is very limited. So yeah, currently we do only one terminal at a time.
Yeah, and David, I'll add to that. I know there are other test beds where this sort of term is head-to-head testing can occur, right? So you might want to have two terminals point, nominally at one another and test. That's a test configuration that OTVT doesn't currently implement. Instead, what we've done is we emulate the other terminal, behind, if you will, or as part of OTVT, and that's what that really allows us to do. is to be able to then drill in a little bit more deeply than, if you just do head-to-head terminals, typically you can't really see quite as much inside of the mechanics of what's going on. So it's sort of a different type of testing. I've seen it done before, but it's not really what OTBT is intended to do.
Okay. Okay. We actually have a question for the audience, and I will present this, and I'll try to read it slowly. What is the interface for executing the test procedures? Will there be a host platform OBC emulator, or will we, as a terminal manufacturer, need to look at our own software for running the tests, as well as collecting and assessing the diagnostics data?
I can take that one. We do not provide host interface emulation sort of on the electrical and structural side of the terminal under test, if you will. I mean, obviously, we provide you a stable platform upon which to put your terminal, but the intention would be if you have any back-end interface or C2, command and control and telemetry monitoring, that would be part of the test equipment that the TUT provider brings along with them.
Molly, anything to add to that, or?
No. Jonah
Okay.
answered it. Yeah.
Okay. Now you mentioned you can replicate a lot of kinds of testing in the OTVT. What kind of environmental tests can you do while operating the OTVT? So, like, what could potential customers, people who are looking to do different things, what can you offer them with regards to environmental tests?
So environmental testing in terms like the Vive, so we don't include any environmental testing. There's no Vive table. Instead we have a line of sight jitter, which is emulated using the fast steering mirror. We don't do the thermal test. Obviously, there's no thermal chamber that the terminal under test could fit in. So we're in a room temperature, but it's a very highly tightly controlled room. So the temperature and the humidity is controlled. Jonah mentioned on the diagram of the facility, it has the laminar flow. We monitor the relative humidity, and the temperature gets monitored and recorded. But we don't do like a thermal test or Vive, and we don't have the pressure test and a humidity test on it, but it's a controlled environment.
As Molly points out, it's a very tightly controlled environment, and we have seen and experienced how when the environment isn't controlled as tight as it is now, we can see variance in the testing. And so the intent, right, is that we have a highly controlled baseline. We can verify your terminal operating under nominal and controlled laboratory environments. And then, we have the experience, and the assumption would be that others would as well, of taking that data, and then you can then apply environmental conditions based on your terminal through analysis. In other parts of Lincoln, we have done environmental testing of the terminal in an environmental chamber, and then do functional testing with other test beds. It's not currently something that OTVT provides. Again, we sort of just separate those two activities and have demonstrated that if you have a proper baseline, you can then extrapolate how you perform in different environments.
I think that makes a lot of sense. That's a really good answer. Let's say I wanted to reach out and set up a test agreement. How long would that take? Let's say I'm on my own program for my company is on a specific deadline, and I've got certain requirements to meet. How long would it take to set up from start to finish to set up a test agreement?
I'll let Molly take a swing at it, because I think she's already done one of these, and we've run this.
So we work with Technology Venture Office here at the lab and the contracting side to set up this test agreement. So we have, as Jonah mentioned in his slides toward the end, we have this mechanism to do this agreement, but we still need to negotiate terms of what type of testing we're doing, how long those tests will take, and obviously there's a cost associated with it. And so I said to set it up, it will take a couple months, including this writing up a statement of work. And in addition to the test date, we want to make, I think Jonah mentioned this earlier too, and that we want to engage with the vendor or the with the vendors to do lots of planning prior. So that makes the success of the test when they come to our test bed more effective. And so we really want the vendor to reach out to OTVT team as early as possible, like earlier in your program planning phase, so you can carve out the testing time and then also planning prior to that.
I think that makes a lot of sense. I mean, obviously, I guess the honest answer, if for any of our facilities, would be it depends. It depends on what needs to get done, how well defined the test requirements are. But I think what you just said, I think makes a lot of sense. Earlier is better, generally with program planning and testing events. I do have another question from the audience. So our audience, if you're still out there, if you're with us, I see that some of us are. Please feel free. We have time. So. We definitely send in those questions. Will there be an option for out-of-band PAT sequence testing, symmetric or asymmetric, wavelength switching need to demonstrate end-to-end testing?
So I think the question is, if you have an out-of-band wavelength as part of your acquisition sequence, can we accommodate that in our testing?
Yes. I would think so, yeah.
So yes, we are familiar with many different PAT sequences and approaches. I was sort of prepping for the briefing. It's like, cool, I say laser comm is great. I skip all the complicated stuff that goes into building it, and then we're just going to test. And as part of OTVT, we do have a pretty flexible PAT. We're actually currently working a program with very flexible PAT requirements, and so the implementation does account for many different approaches to acquiring the laser comm link, and so that is certainly part of the approach. Getting back to the earlier question, right? If you've come in with a really exotic or novel way to do acquisition or any aspect of laser communication, that's going to extend the time it takes for us to be able to help you out in that testing, right? So we have a pretty comprehensive portfolio of capability, tools, knowledge, experience, whatever you want to say, that doesn't preclude someone coming in and asking, boy, I really like to do something new, and can you help us do that? We certainly can, but that's going to extend both the commitment, right, the scope of work that it takes, and the schedule to implement those things. And so the broadest answer is we probably have what you're looking for, and if you don't, we might be able to help you get to a test set that can.
Okay. Another question from the audience. So questions are coming in, and this is a question I was curious myself. How long and what was the ROM investment did it take to develop OTVT to its current state? And can non-US based companies or institutions test their terminals at OTVT? So let's say I'm a French company and I've got some laser comm technology that I'd like to test. How do I? Yes. So that's a lot of things. How much did it cost to set up?
Yeah. So OTVT in its current instantiation really represents almost 2 decades of investment. It's done nearly 24 test events in varying forms. And each, as I said, each of those events has sort of added to the capital investment on it. At this point, it's tens of millions of dollars of investment that the government has made on this test set. So it is really a pretty unique asset in that it has accumulated quite a lot, both of physical and cost investment, but also experience and knowledge, right? And those things, I think, are sometimes hard to quantify in a dollars point of view. With regards to testing from foreign nationals, I will confess I am not the contracts expert, and I do not know exactly the bounds of where the test agreement limits tap out. I suspect it does need to be a domestic organization or a company with a subsidiary that is domestic, and I know we have done activities in that manner. But David, maybe we'll take that question and we can put it into the TVO machine and see if we can send out an answer after the fact. But I'm pretty sure there's going to have to be some domestic entity to come in and use a test agreement. I know that's what the chart says. Yeah.
Yeah, I was about to say somebody has luckily gone back to the charts and said, "Hey, we wrote it right there, a domestic non-governmental agency." But to your point, I do know that there are a lot of companies that have U.S. subsidiaries or U.S. branches that may have that capability to do that kind of work. I know we're running short on time, but Molly and Jonah, do you guys have time for one more question from the audience?
One more, sure. Yeah.
All right. Not from me. What is the operating environment during testing, i.e. will the lights be off? Otherwise, will we require solar filters for background light source rejection?
Right, I can answer. So the lab environment, we can turn off all the lights. I mean, there's some reflection off of the screens that we have inside the lab, but we can mitigate that. There are other ways we can mitigate, but yeah, we can have the room darkened with all the lights off in there, and we have done that type of test.
Will they require solar filters for background light source rejection? Sounds like no.
I don't think we had that case where we had to use, where the TUF provider brought in the solar rejection. Yeah.
Okay.
And we don't currently have a solar emulation.
Yeah.
We do have interferer type capabilities to some varying degree, but there isn't like a emulated sun in the test bed. That is a test configuration that I've seen people use before.
Okay. Well, Molly and Jonah, thank you so much for your time, for discussing the OTVT with us from Lincoln Lab. And ladies and gentlemen, thank you for joining us. The session will be recorded and available on the FLC website. And thank you and have a wonderful day.
Thank you, David.
Okay.